In this session, I would like to talk about memory organization. Why we have to organize the memory is a question. I will tell you. So memory is very important parameter for us in instruction execution, correct? We will be storing our instruction in memory, right? Assume that let's say we have main memory, okay? So if you have only main memory, assume that let's say all your program is available in the memory. That means all the instructions are already available in the memory. Then to fetch that instruction, generally it takes 100 clock cycles because memory access time is very lengthy. That means it takes a lot of time. If you compare with arithmetic logic, understand, that means to add two values which are in registers, that takes only one clock cycle. But if to get the data from main memory, that takes hundreds of clock cycles. Then you know one thing, in pipelining we have 5 stages. Did you remember? Fetch, decode, execute, memory, write back. In the memory stage and instruction fetch, we are accessing the memory. At that time, if you take 100 cycles, then probably you can't get the benefit of pipelining, right? Did you remember? Already I told you that in pipelining we can get benefit if every stage has same delay, right? If there are uneven delays, so because of one stage, other stage has to wait, correct? That's why you don't get the advantage of pipelining if you have only main memory. Now, so that's why we are going to introduce a memory called cache memory. So what is the problem with cache memory and how to use it is the story of this memory organization. And before going to that cache memory details and everything, we'll see just rough idea about current technologies. Currently, we have three kinds of memories. One is secondary memory, second one main memory, third one is cache memory, which we are going to discuss in very detail. Cache memory. So we'll see the properties of these memories. The secondary memory is actually, it can have lot of data, okay, gigabytes of data, terabytes of data. But the problem with secondary memory is, the speed is slowest. That's the problem. That's why we can't directly connect our CPU to this secondary memory and we can't do the things. That's why secondary memory is not directly connected to CPU. Understand? So that's why main memory is introduced. Main memory is built with a different technology than secondary memory. We know that, right? So secondary memory generally uses electromagnetics. That means, you will have, magnetic plate and we write on that plate, right? So that's why here you have mechanical and electrical two things. So, and we use electronics and mechanical movement, right? Already I told you in DBMS. So there will be input output head, then we have to move it. So because of that, it takes a lot of time. That's why. So I can say that it takes thousands of clock cycles if you use it with respect to CPU clock cycles. If you fetch data from secondary memory, it takes 1000 to 10,000 clock cycles. So we should not directly connect our CPU to secondary memory. That's why we use main memory. But the difference between secondary memory and main memory is volatile. That means when you switch off your computer, then automatically data will be lost. Before that itself, we have to transfer entire data back to secondary memory. That's why secondary memory is essential. Okay, but don't directly connect it to CPU. That's why we connect our processors to main memory and we try to access data from first main memory. If it is not available, then we'll go to secondary memory. That's why this kind of hierarchy, secondary and main. Now if you see the speed, it is better than secondary memory, and I can say the speed of the main memory, if you access the data from main memory, that takes some around 20 to 100 clock cycles, whereas arithmetic takes only one clock cycle. Understand? The decoding and execution and writing the data into the registers, everything takes only one clock cycle. But if you use main memory to access the data, still that takes some 100 clock cycles. We have to bridge the gap. Finally, we have to design a system such a way that memory access also takes one cycle, so that we can run our pipeline full-fledged, right? That means there will not be any stalls. That is our goal. Example, if there is a memory stage. In the memory stage also, if you can get the data in one cycle, then only we can get the advantage of pipelining and your computer works very fast. Understand? That is the goal. Finally, in one line I can say, you organize your memory such a way that even your memory access also should take one clock cycle, but main memory cannot support that. Main memory definitely takes 20 to 100 clock cycles. Then what to do? That's why the special kind of memories are designed. They are different from main memory. Okay, so they are cache memories. The cache memory model is different. That means, the way they are prepared are different. So what they to prepare that cache memory is we use a technology called static RAM technology. Okay. Now to create this kind of main memory, we use dynamic RAM technologies. Okay. So that's why main memory is DRAM and cache memory is static RAM. So we know that hard disk is made of magnetic disk, right? So that is a model of secondary memory. We have three models now. But the problem is, sir, why don't you directly have cache memory? Why you want to have main memory? Please discard that main memory part. So if I discard main memory part, what's the problem is, cache memory, if you use this SRAM technology, that means, static RAM technologies, then that takes, the cost is highest. That's the problem. So you can't afford that much cost. So we have to use sometimes main memory also. That's why main memory cannot be discarded, because the cost of cache memory is very high. Okay, if you see the cost chart, you will understand. Cost of disk lowest, cost of main memory moderate, I can say moderate, cost of storing the data in cache is highest, the cost per bit I am saying. Okay, so if you want to store 1 bit, the cost is here cheapest, here moderate, and highest. Now we'll see the size. Generally cache size will be smallest, okay, because the cost is very high if you have huge size. Understand? Now second thing, this main memory sizes will be moderate and the secondary memory size will be biggest. That is what current technologies support. Now we can't have very big cache for cheaper cost. Understand? That's why. So usually we are going to build cache of smallest. Now finally I can say, you have cache, but the size should be smallest. We can't have very big cache. Okay, and sometimes if you have very big cache, then the access time cannot be fastest. That's a problem. It's a trade-off. So that's why cache should be very small, so that you can make it very fastest, and at the same time cost also can be manageable. Understand? The reason is the cost of this cache memory per bit is very high. So now finally, that's why people realize that we use secondary memory, we use main memory, and we use cache memory. We can't avoid secondary memory. Already I told you, when power is off, then definitely everything, all the data should go to secondary memory. That's why don't touch it. It is compulsory. Now, but don't try to access every time data from secondary memory. That's why whenever the power is, your computer is switched on, then eventually we take some of the important data and we keep in the main memory. Now similarly, so from the main memory we transfer some data to cache. Okay, that is what the hierarchy we use. Okay, why we get benefit of hierarchy we will see. Now let me summarize what is going to happen. We have cache, we have main memory, we have secondary memory. We have to organize them. Okay, we will see how to organize them. Okay, and so that we can get the maximum benefit. Generally, to understand the organization of this cache and main memory and secondary memory, you should understand two basic principles of program. Programs have this behavior. One is temporal locality, second one spatial locality. So what is temporal locality, sir? Example, when you write a program, then there is a high chance that it has a temporal locality. That means what's a temporal locality? That means, so your program is going to refer a memory location, otherwise an instruction so many times. The same instruction your program is going to refer so many times. That behavior is called temporal locality. Sir, example, let's say you have a for loop, you have a while loop. In the for loop you will write some instructions so that instructions will be repeated, correct? So that means the for loop, otherwise while loop, otherwise most of the times when you have a function calls, example, when you repeat the function calls, then you will be going to same memory locations again and again. That's why, so we say that such kind of programs will have temporal locality. That means that's a behavior. Okay, now the second kind of behavior program generally have is spatial locality. The programs also have another behavior, that is when they access some memory location X, then there is a high chance that they are going to access the next location, because most of the programs people write so that they are sequential. That means they try to write instruction. Generally it's a general behavior. What people observe is, when you have written a program, let's say if that access, that means that executes instruction 1 which is at memory location 100, Then after that it will go to the next memory location 104. After that I3 will be executed 108, but eventually very rarely there will be jumps. That means what is normal in the program execution? Going one by one. That means in a sequential way. What is abnormal and which is generally done rarely? That is jumping. So we jump rarely, but we go sequentially regularly. That's why we say that we have a behavior called spatial locality. In one line, that means whenever your program is accessing instruction number 1, which is at memory location 100, there is a high chance that there is going to next immediate instruction which is at 104. Similarly, if your program access a memory variable x, okay, which is at 100, then there is a high chance that it is going to use another variable called y, which is immediate. Okay, even your compilers plan the data like this. Example, if you write a program, then all your data items which are related will be stored linearly one by one, so that they will have spatial locality behavior. Understand? Finally, of course, you are a good programmer and you can easily understand that whenever you write a simple program, then they will have these two behaviors, right? Temporal locality and spatial locality. Understand? Let me revise. Temporal locality. When you access an instruction, again and again if you access the same instruction, then we say that you have a behavior called temporal locality. Similarly, we have spatial locality. That means when you access an instruction, there is a high chance that you are going to access the immediately next instruction. Yes, so that is spatial locality. General programs will have these two behaviors. So by keeping these behaviors, then if you build your memory organization, then you are going to get the benefit of the reduction in the memory access. Why, we will see. For that I will give you an analogy. What is that analogy is, let's say you are every day you are buying some of the household items at nearby your shop. Okay, there is a small shop which is just in front of your house. This is your house. Okay, now this is a supermarket, a very big supermarket, which is only one for entire city. Let's say you are in Hyderabad. This is your house, and this is a colony. In the colony you have a shop, and this is your city. In the city you have a big supermarket. Now supermarket contains everything, shop contains few things. This shop owner generally brings his items from again supermarket, because everyone has to go for supermarket. Now let's say you are in this house, and in the early morning what you have realized is there is a paste is missing in your house. Paste is over. Then what you do generally, tell me? Yeah, definitely you will go to this shop. You don't go to that supermarket because the distance is, let's say, 20 kilometers. You can't travel just for after all paste, right? So that's why generally you will go to shop, and in this shop it is available, then you will take, otherwise you will go to the supermarket, right? So same way. Now one more thing, you tell me what this shop has to keep so that it can reduce all these colony people's it can reduce their time, it can save their time. Example, let's say this shop is specially designed for the people who are staying in this colony for their benefit. Then to save the time of these colony people, that shop should have very important data like paste, coffee powder, everything, but it should not have. Example, let's say this supermarket contains everything, like maybe they have a rare item that is called I can say a very rare medicine for cancer. Okay, a rare medicine for cancer. Only in 1 lakh only one person will take that medicine. Okay, but some of the people like here also want that medicine. Now this supermarket, this shop owner cannot keep that rare medicine here, because if he keeps, then what happens? The space will not be sufficient, because if he keeps this kind of rare medicine, he also have to keep so many such things, but he can't keep. Correct? So he has a space limitation, very small shop. So that's why what he will do is he will keep the items such a way that they are regularly, that means they are used by majority of the people. Example, let's say paste is used by everyone, he will keep paste. And coffee powder is used by everyone, he will keep coffee powder or tea powder. right? Milk. This kind of important data he will keep rather than that rare medicine for the cancer. Otherwise, TT balls. Only few people play TT. He doesn't know who will use that TT ball, right? He can't. And one more thing. Let's say you can imagine like this. There is a TT board also, table tennis board. The size is huge. He can't keep the TT board here. But some of them in this colony wants to purchase it. Then we can't keep here because this shop has to keep only important things, then only it can give the benefit to everyone, right? What if this shop is completely filled? What is your doubt is, if this shop is completely filled with table tennis board and volleyballs, footballs, everything, then what happens? Only 1% of the time people are going to buy them, but 99% of the time people are going to ask for milk, coffee powder, but we did not keep them. Why? Because the space is not sufficient to keep everything. So what we did is, we kept these sports items, which are in India generally people very rarely use sports items, and the pens, papers, everything we did not keep because there is no space in the shop. If the shop owner maintains like this, then definitely that's not a good organization, correct? Now you tell me, what should be kept in this shop? Definitely important data, right? So that is what even we have to do. Now we are going to build our main memory exactly in the same way, right? The important things we are going to keep in the cache, so that, see, this is going to be, now let's show the analogy. This is your main memory, okay? Forget about secondary memory. So I'm showing the relation between your cache and this main memory. Main memory is nothing but supermarket. Cache is nothing but the shop here, which is nearest to your colony. So now what the goal of the shop should be, 90% of the time, otherwise 95% of the time, the people who are around this shop should get success. And however, he can't achieve 100% success, because for that all that items of the supermarket he should keep. That's not possible, because we don't know. Assume that, let's say, the people in the colony can ask anything, but they don't have a random behavior. They have some very regular behavior. What is that? Drinking milk and brushing every day and bathing every day. For this kind of regular activities we require some of the items, right? If you can keep them, then you can easily understand that, otherwise the shop owner can easily understand that 90% of the time people's behavior, or whatever the people buy, they are popular, right? Regular. Only 10% of the time these colony people or anyone in the reality also ask rare items, correct? So at that time, 10% of the time, what that shop owner can say is, my dear someone, let's say Raju, tomorrow you come, I'll get it. It's not available now. I have to go to 20 kilometers and I have to bring the data from the supermarket. Come please after 1 hour. So only that kind of 10% people, otherwise the only for that kind of 10% requests, we will be making them wait. But 90% of the time we are immediately giving the data, so that the shop will successfully work, right? In the same way, the goal of the shop here is to reduce everyone's time. But every time the shop says that I will go and to supermarket and I will get it, that means we say that only 20% of the time whatever you ask, let's say, that data is available in the shop, then that's a bad design, correct? So fortunately we can achieve 90 to 95% of the hit ratio. The reason, programs also having the same kind of regular behavior. What is that? Temporal locality and spatial locality. As a human being, you have a regular behavior. Similarly, program also, which is written by human being, also possesses that kind of regular behavior. Okay. So what that is? Asking, that means accessing immediate data items, accessing same data item. These two things very regularly programs do. That's why I can say that we have to target these two behaviors and we have to design our system. So we are going to design our system with that. Okay. Now we'll see the idea about this memory hierarchy. Generally, people arrange this memory in a hierarchical way like this: level 1, level 2, level 3. Now how data will be typically accessed? You see, this is your processor. Now you have some memory reference M. Okay. That means you want to access a memory location M. Then first we search in level 1. If that is not available, then we'll go to level 2. If it is not available, then we'll go to level 3. This is the way we follow. Okay. Second thing, case number 1. Sir, what if data is available in level 1? Then we take it, right? Nothing to discuss. Sir, what if data is not available in level 1? Then we say that it is level 1 miss. What are you going to do? Then we'll go to level 2. Sir, in level 2, let's say there is a hit, that means data is available. Then what are you going to do? Then at that time, we transfer data from level 2 to level 1. Slowly you will understand what is the reason for that. So we transfer data from level 2 to level 1. Let's say it is X. Then after that, we access the data from again level 1. That's it. Sir, what if data is not available in level 1, not available in level 2, but available in level 3? Then what are we going to do? Simple. Since data is not available in level 2 but in level 3 it is available, then simply first step, transfer the data from level 3 to level 2. Then transfer the data from level 2 to, now data is available at level 2, right? Now it's like a data is not available in level 1, data is available in level 2. What you do? We move data from level 2 to level 1. Then now data is available in level 1. Then you access it. So this is the way generally typically your memory is organized and accessed. Understand? So that is one thing. We use two keywords most of the times. One is hit, second one miss. In any level, let's say you are in some level I. So whenever hit occurs, that means data is available in level I. When you are searching in level I and data is not available, then we say it is miss. Understand? And our target should be, did you remember one thing? Always you remember this thing. This level will be, this is let's say level 1, this is level 2, in that way. So any number of levels we can have. So in level number 1 actually the access time will be very less. That is, access time is very less. When we go to level 2 or level 3, that will become, access time will become more. That's why most of the times we should not visit level 2. Always we should take the data from level 1. That's why we have to maintain important data, and I can say popular data rather than important. Popular data. Popular data is nothing but data which is visited, otherwise accessed very regularly. So definitely what can I can understand is 90% of the time your program access same data. That's why. So that is the meaning of temporal locality and spatial locality, correct? Because of that, if I exploit that and if I use that for my advantage, then definitely 90% of the time we can get the data in level 1. Such a way we have to fill level 1 eventually. Okay. So we should understand the program and we should understand the behavior of the program and we should understand what is important, what is not important through some means. I don't know like exactly. So a particular program uses which data, no one knows, but we should use some statistics, otherwise we should use some strategies. And based on that we should somehow assess that this is a popular data, this is not a popular data. We will see how we assess it. Okay. So this is about level 1, level 2, level 3 and their access. Now apart from that we have one more thing. So that is, we transfer the data from any level to any level usually using a block. That means we do block transfer. I will explain what does it mean. Let us take only two levels. Okay. Because at any time we are dealing with only two levels, correct? So let's say you have two levels, level 1, level 2. So when you are dealing with level 1 and level 2, and assume that let's say level 2 has data, level 1 doesn't have. You are searching for that data, okay? You are looking for data which is not available in level 1. Then we will come to level 2. But it is available. I am talking about this case, okay? So in this case, what you will be doing, you will be transferring the data from level 2 to level 1, right? I said that. But rather than transferring only that data, apart from, you transfer more. Why? So that we can exploit this concept called spatial locality, right? So what is spatial locality? Whenever a program refers a memory address M1, then most probably it will be accessing the next M1 plus 4, after that M1 plus 8, in that way. Now whenever there is a miss of M1, then definitely M1 plus 4, M1 plus 8, so on, everything might be missing. Then what you do is you bring that kind of bunch of memory locations, so that next time we can easily, we cannot get the miss. Understand? I will give you an analogy. Example, let's say you have, one, did you remember that shop? Let's say Raju is a shop owner, very smart. Okay, he's very smart. Now, one day what happened? You visited this Raju's shop and you asked him, milk packet. Okay, milk packet. Then Raju searched entire shop, but there is no milk packet. What he did is he went to supermarket, but rather than one milk packet, he brought some 10 milk packets and two otherwise 10 coffee packets and 10 tea packets. Then you ask me, you ask Raju. Raju, you need only one milk packet, right? Because customer wants only one milk packet. Why you brought 9 other milk packets and coffee packets and everything? Because when someone asks milk packet, there is a high chance that in the next immediate accesses, the same person might ask another milk packet. Maybe otherwise immediately, because someone is asking milk packet means it's early morning. But I don't have other milk packets. Then after this fellow, next person will be definitely most probably is asking milk because it's morning. Morning everyone will drink tea, so everyone is going to access milk packets. Similarly, they not only ask milk packet, the same customer, let's say this customer is Rani. Once I give Rani milk packet, what she will do with that? Maybe she drinks tea or coffee. Then most probably once I give her tea milk packet, immediately her next instruction might be, brother, please give me tea packet. Then where should I go? Again, should I go there? No, don't do that. So that's why what Raju is saying, that we should understand the neighbor, we should understand the programs correctly. Once any program access any memory location, then there is a high chance that it is coming linear, right? After 100th memory location, maybe that location contains instruction 1. Then after executing instruction number 1, what program will do? It will execute I2, then I3, then I4. Then what we do is, we somehow understand that, so these are all related data and we fetch it. That's why rather than one data unit, we bring a set of data units. That means block, entire block we transfer. If I do that, sir, what is the block size? Generally block size will be decided by the designers. Okay, so it depends on the program's behavior. What they do is they observe some of the programs and they do I can say that is called speculation, otherwise simulation. Using the simulation, they understand what will be the ideal block size, because we can't say, because it depends on the program, right? So that's why what they do is they run some template programs, otherwise benchmark programs, and based on their requirement they will decide what should be the block size. Sir, I have an idea. What if I take very large block size? Then I never get cache miss, sir, right? That's not possible, because this level 1 is going to have very small size, correct? Then if you take very large block size, that means if you say that block size is 100 words, there are two reasons. One is unnecessarily, to transfer 100 words from level 2 to level 1, we should access this memory, right? After some time I am going to tell you what is the time taken for accessing 100 words. Accessing one word takes 1 nanosecond, then maybe accessing 100 words might take 100 nanosecond. Then you are wasting lot of time, right? So by wasting lot of time and you are keeping that 100 words here, then after that what can happen? Your program might not think that these 100 words are related to that program's execution. What that program might think is, otherwise what that program might do is, it might suddenly jump. Understand? So that's why maybe otherwise only for that program only 3 or 4 nearby locations are important. It is going to visit only that 3-4 nearby locations. After that it will be jumping. Then all that the effort which you made to fetch that 96 words will be waste, right? Similarly, I will give you the analogy here again. Raju is the smart shopkeeper. Someone asked milk, right? Then what he did is, so he brought all the remaining things. Like how he brought, you see, whenever you ask milk packet, what he did is, so what people do with milk packet, maybe they drink, after they drink milk or with tea, then what they do, maybe they go for breakfast. Then he brought some noodles, because he thought, because whoever drinks milk, then maybe after that they do breakfast. Then he brought noodles. Then after that what he thought, whoever takes a breakfast, after that after some time they will prepare lunch, then he brought all the vegetables, everything. Then after that later he decided that in the night probably they require again some data item, something whatever. In the night probably they watch some movies, then to watch that movies then maybe they require CDs. He brought some movie cassettes, understand? So if he does all these things, what can happen? The person who took milk packet, maybe he might not ask anything else and he will go to the house and he will make he will prepare a tea. Then after that suddenly he might get call, and because of that call immediately he will run away to his office. Maybe he is not doing any lunch preparation in house, maybe he is not doing anything in the night, everything he will be getting in office. If that is the case, your guess is wrong, right? But unnecessarily you brought noodles, vegetables, everything for him, but he is not behaving like as you are expecting, right? So that is what usually occurs. Sometimes we cannot exactly predict what is the program's behavior exactly, right? So what are the relevant information and what is not relevant information, it will be quite difficult. That's why what people do is they will decide the block size by observation, by running some of the programs. Okay, so that's why that is not our job. Okay, assume that let's say some block size is fixed, understand now. So finally one important thing you should remember is only one thing: whenever miss occurs in the level 1 and when you go for level 2, then while bringing from level 2 bring a block, that's it. Block size is let's say 4 words, then we will be fetching 4 words. It takes definitely some time, but there is advantage, though you are wasting your 4 words of time, transfer time, but in the subsequent execution, subsequent references, always we get hit. In that way we can improve the hit ratio. Okay, so this hit time we can improve, understand? Otherwise if you bring only one word, next time what might happen, so he will access the next location and that might not be available in the level 1, then again you will go. Then again the one thing is, sometimes there are two things we will discuss. Whenever you are accessing one memory, then each word you access takes some time. Okay, remember it. That means if you access one word, it takes 1 unit of time. To access 2 words, it requires 2 units of time. If you access 10 units, 10 words, then 10 units. Apart from that, there is another thing, preparing the memory. Try to understand. Example, you have a memory and you want to access one word. Okay, it will be like this: go there, prepare, enable everything related to that memory and prepare your register and get the data. Okay, that is the idea. But what if you have to access 4 words? Then first of all, go there, prepare this memory, enable this memory, start accessing. That means that is called memory latency. First of all, prepare this memory for fetching the data. After that, take one by one. Okay, so here to take 4 units of data, there will be some amount of time. Apart from that, to prepare this memory, initial latency will be there. Okay, so that initial latency will be high if you do that things every time. What I am saying is, example, case number 1. In case number 1, you are accessing only one word. Then for that, what are you doing? You will be going to memory. Memory, be ready. Okay, we are saying be ready. That is called memory latency. Okay, that means we are preparing the memory to fetch the data. Fine. Once everything is ready, once this memory is ready and all the registers which are required are ready, then data will be transferred. Assume that let's say you are transferring one word, that takes 1 second. Then how much memory latency initially? Let's say 5 seconds for preparing your memory. Then 5 plus 1, 6 seconds. You are wasting how much time to fetch one word? 6 seconds. Now take the second case. In the second case, you are fetching 4 words at a time. That means you are transferring 4 words. If you transfer 4 words, what is going to happen is you will be preparing the memory. My dear memory, be ready. It takes how much time? 1 second. After 1 second, now this memory is ready to give you data and take one by one. First word, 1 second. Sorry, memory latency 5 seconds, right? So first to prepare your memory 5 seconds. After that, fetching the words one by one. Fetching the first word 1 second. Fetching the second word 2 seconds, 1 second again. Fetching the third word 1 second. Fetching the fourth word 1 second. So total time is 5 plus 1, 6, 7, 8, 9. So 9 seconds. But whereas if you do that one word by one word, that means every time whenever there is a miss, then only you go and fetch it. That means you are doing lazily. Okay, if you don't do block transfer, what is going to happen? We will see again. Then you want to take 4 words, but not at a time, eventually one by one. Okay, whenever there is a miss will come in that way. 1 plus 1 plus 1 plus 1. Okay, start. First word. For that, prepare the memory. My dear memory, be ready, and everything will set up, all the appropriate signals, everything. So that is memory latency. Usually that memory latency is significant. Understand? So remember one thing, your main memory especially, that has lot of memory latency. To prepare it for getting the data, you need lot of time. That is, let's say, 5 seconds. Okay. Then plus. Now you are taking only one word, right? Then 1 second. 5 plus 1, 6. So for one word you are taking 6 seconds. Then you will come back again for second because second word is not available in the cache. Then for that again you will come. This time prepare the memory, 5 seconds. Again 1 second for data. So in that way 4 times 24 seconds. Here only 5, 6, 7, 8, 9. That's why it is better to transfer the data in blocks. However, because your program is going to take it in the subsequent references. Understand? But the size should not be very large. Don't say that I will keep very large block. Then so that all the data items in that block may not be relevant for this program. At that time, unnecessarily you will be disappointed. Understand? It's like supermarket. That fellow wants only milk, but you thought he will be staying entire day in the house, and you brought him everything for that particular day. Then what he did? He went to office. Then whatever the items you brought for him, everything will be wasted. In that way, rightly predicting is important. Similarly, that's why block size is important. Okay. Don't arbitrarily increase it. You don't get benefit. So what people finally realized, I will tell you. So they took, initially they took only one word. Okay, generally. So they tried one word, they tried 2 word block sizes, and they tried 4 words in the block, they tried 8 words. After that, slowly they realized improvement in the hit ratio. First word, only 1 word block, 2 words block. If you see, there is a improvement in the performance. Again improved, performance suddenly started decreasing. Why suddenly performance gets increased when you increase the block size? Maybe in the process of increasing the block size, you may be fetching unnecessary information and you are wasting the time and you are not getting the benefit because no one is accessing the data. Understand? So that's why, so there will be some, I can say only for some certain amount of size we can increase the block size. Okay, there will be one ideal case. After that, your performance will be decreased. So here you have to fix the block size, and that is of course not a very important for gate. Okay, just remember this fact enough, because some of the students will have this kind of questions in their mind. Sir, why can't we increase the block size arbitrarily so that always we can improve the hit ratio? It will not be possible. After some time your hit ratio will be decreased. Understand? That is one thing. Now, so finally you understand these two important things. One is data will be transferred in blocks. Okay, that is one thing. Second one, the block size should be suitably fixed so that we get the optimum hit ratio. All right.